So hello class, our topic for today is about Taylor series under Advanced Engineering Mathematics. So to give you an overview about this topic, okay, so this Taylor series is a powerful tool in calculus used to represent a function as an infinite sum of terms calculated from the values of its derivative at a single point. So given this function, okay, we're converting it into infinite sums or infinite sum of terms or series. So and the values from these terms, okay, is calculated from the derivative of our given function. Okay, so if a function f of x is infinitely differentiable at x equals a, then the Taylor series of this function is f of a plus f prime of a times x times the quantity x minus a all over 1 factorial plus f double prime of a times the quantity x minus a all over 2 factorial plus f triple prime of a times the quantity x minus a all over 3 times 3 factorial plus so on and so forth. Or we have this general formula, the summation of from n equals 0 up to positive infinity, okay, of f of n prime of a over n factorial times the quantity x minus a quantity squared. Okay, so this will be the general formula of our Taylor series. Okay, and take note, if our a is equal to 0, then this is called a Maclaurin series. Okay, again, if our a value is equal to 0, it is called the Maclaurin series. So let me give you a general workflow for this Taylor series. Okay, so by following these steps, you can easily get or find the Taylor series of our function. Okay, so in step 1, you should identify the function and the expansion point, meaning you should have the given function f of x and the expansion point, which represents our a value. Okay, expansion point. Again, if a is equals to 0, okay, it is Maclaurin series. Otherwise, if it is not equal to 0, then it is a Taylor series. Okay, next, step 2, compute the derivatives at x equals a. So the first thing you need to do here is to get the or differentiate our given f of x or given function. Okay, it's up to you. Okay, so it's up to you how many times you will differentiate it, as long as from your differentiation, okay, you will get a certain pattern of it. Why? Because based on your values in differentiation, okay, you will derive the general formula for our Taylor series. Okay, general formula of the series of the function. Okay, based on the function rather. Okay, so once you get the derivative, like let's say you get the n derivative, okay, or the f of n prime of a, okay, so you will use those values, or yeah, so you just you will plug those values in our Taylor series formula, and that will be your step number 3. Okay, just recall the Taylor series formula and substitute the determined values. Okay, those values that you got from differentiation. Okay, next, step number 4, write that truncated version and simplify to get the general formula. When we say truncated version, this is the first few terms from the series. Okay, or it is the expanded version of our series formula, Taylor series. Okay, so expand several terms, no? So recommended 3 to 5 terms, okay? So actually it's up to you, no? It's up to you how many times you will expand, okay? As long as you can find or get the general formula of the series, okay? After expanding those terms, so simplify term by term, simplify each term, okay? Next, while simplifying, identify the patterns, okay? Look for the signs, the positive sign, negative signs, the coefficients, and the powers, okay? And from that, you will come up with the general formula of the series, okay? Next, number 5. So actually, you from this step number 4, you already have the Taylor series, okay? You already have the Taylor series, the formula, general formula. If you've been asked to get the general formula for the Taylor series, okay, or yes, the Taylor series, the general formula, so you just simply apply those first 4 steps, okay? So this following step 5 and 6 are optional, okay? If you are being asked to get the radius of convergence and interval convergence, so apply this remaining step, okay? So for number 5, you will find the radius of convergence and interval convergence. So it's either you will use either ratio test or root test, okay, from to your general term, okay. So this is the following formula. So we have this ratio test, okay, and this is the root test. And for the formula of our internal convergence, so we have this a minus r, okay, up to a plus r. So again, it is the interval, okay, interval convergence. So that's why it is written as this form, okay. And lastly, so we have this this last step, okay, determine the convergence at the endpoint of interval. So from our internal of convergence, okay, we will evaluate each of the endpoint, okay, endpoint from the left and from the right, okay. Evaluate if that point converges or diverges, okay. So that you can conclude, okay, or finalize the full interval convergence, okay. So in this number 6, no, in this step 6, you just simply apply the convergence test, okay, any test for you to determine if the endpoint is convergent or divergent, okay. So let me give you an example. So example, okay. Find the Taylor series for f of x equals ln of x centered at x equals 1. Okay, so apply the first step, identify the function and the expansion point. Okay, so we have given f of x function, so we have ln of x, and then our expansion point is 1, okay. Our a is 1, which is also equal to x, okay. And since our a is equal to 1, or since our a is not equal to 1 rather, equal to 0 rather, then it is a Taylor series, okay. Next, step number 2, compute the derivatives at x equals a. So we already know that our x is equal to 1, okay. So to apply this second step, let's start with differentiating our function, our original function. So let's differentiate this okay, let's differentiate this, okay. So if we get the so using this after you differentiate this, okay, you evaluate it, no, by our x equals a. So for f of x, okay, we have ln of x, and then if you evaluate it, okay, so the answer will be 0. If you evaluate it if x is equals to 1, okay, so the answer will be 0. Next, first derivative, okay, from the ln of x, okay, so we have 1 over x. Evaluating it, we have equals 1, okay. Next, second derivative, we have negative 1 over x squared, and by evaluating it, so we have negative 1. Third derivative, 2 over x cube, okay, after evaluating it, so we have 2. Fourth, it should be fourth, okay, it should be fourth. Sorry for the typo. It should be fourth derivative, okay, it should be fourth derivative. Fourth derivative, it should be f of, we can write it as, wait, we can write it as f of f fourth derivative of this is equals 2 times 3, negative 2 times 3 over x to the fifth, okay. So yeah, and evaluating it, okay, if x equals 1, okay, so the answer will be negative 6. And lastly, we have the fifth derivative of this function, okay, so we have negative 2 times 3 times 4, I mean negative times the quantity 2 times 3 times 4 all over x to the 6, okay. And evaluating it as x equals 1, okay, so we have 24. Okay, so we're done in our second step, okay. So let's proceed to our third step. Plug the values, the following values in our Taylor series formula, okay. So recall the formula for our Taylor series. This is the formula, right? So from this, okay, apply those values that we determined. So get few terms of this series. So if n equals 0, okay, if n equals 0, so we have f, if n equals 0, okay, so we have f of x over 0 factorial times x minus, what is a? We have 1 raised to 0, okay. We all know that f of x, or f of a rather, f of a is equal to 0. So we have 0 here, okay, over 0 factorial, okay, multiplied by x minus 1 quantity raised squared, okay, quantity squared, okay, no squared, it's quantity 0, okay, quantity raised to 0, okay. So in short, the answer here is 0, right? The answer here is 0. Next, if n equals 1, if n equals 1, so we have f prime of a over 1 factorial times x minus 1 raised to 1. So our f prime of a is this one, okay, f prime of a is this one, and then plug it in our formula. So we have 1 here over 1 factorial times the quantity x minus 1 raised to 1, okay, this one. Just plug it, okay, continue, okay. If n equals 2, okay, if n equals 2, so we have f double prime of a over 2 factorial times x minus 1 raised to 2. Okay, so this one. Okay, our f double prime of a is this one. Okay, just continue the process, okay, until you use all the terms or use all the determined values that you have. Okay, so after expanding, okay, so actually we're starting to do the fourth step. Okay, write that truncated version and simplify to get the general formula. So the following, okay, these are the truncated version. Okay, truncated. So we are already expanding our series. Next, after expanding, simplify each term. So if you simplify this, the answer is 0. Okay, if you further simplify this will be the answer. Simplifying this will be the answer. Yeah, this one. So on and so forth. Okay, next, from after you simplify, okay, let's evaluate this. Okay, evaluate this one. As you can see, no, we have this pattern, no? Our sign changes. So we have positive here, we have negative here, we have positive here, we have negative here, positive. So next, for the coefficient, so at the start we have I think it's 1 over 1, yeah, or simply 1. Next, the coefficient here is 1/2. It became 1/2. Then it became 1/3, 1/4, 1/5. Okay. Next, how about the powers? Okay. So we have originally we have 0 power here. Then we have 1 here power, 2, 3, 4, 5. So if you're going to analyze these patterns, so we will be arrive at this certain general formula. Okay, and that is the summation from n equals 0 up to positive infinity of negative 1 raised to n plus 1 all over n times the quantity x minus 1 raised to n. Okay. So this will be the final answer, or if you're been asked, okay, if you've been asked to find the Taylor series, the general formula for the Taylor series, and for us to evaluate what will be the possible values for our x, so we need to proceed in the remaining steps 5 and 6. Step 5 and 6. Okay. So for step 5, find the radius of convergence, and also I forgot to and the interval of convergence. Okay, interval of convergence. So to do that, we must use either ratio test or root test, okay, to evaluate the limit of our general term. Okay, given that we have this general term, okay, our general term is this one, right? So we use this ratio test, okay, to evaluate the limit. So after evaluating this, you will arrive at this answer, x minus 1. Okay, so x minus 1. So take note in ratio test, when the limit is less than 1, the series convergence. Knowing that idea, we form we form an equality, an inequality, okay, rather, an inequality, which is x, the absolute value of x minus 1 less than 1, okay. So this is our inequality, okay, inequality. And from this inequality, our radius of convergence is equal to 1, this one, okay. And for interval of convergence, we will be using this formula, a minus r and a plus r, where r represents the radius of convergence, okay. And since we already have value for a and r, so our a is 1, right, and the value for r is also 1, so we have 1 plus r here, okay. So the interval of convergence will be 0 and wait, okay, so this is 1 also. So the interval of convergence is from 0 to 2. Okay. It is an open interval, okay. So another take note, okay, take note of this note, okay. If your limit, okay, if your limit follows this pattern, okay, pattern of inequality, I mean, again, if you apply ratio test and then you end up with an inequality written in this form, the absolute value of x minus a, okay, less than r, oh. So this means, okay, this already tells you that the series converges when x is within the r units from the center A, and it gives you direct value for the radius of convergence, okay. So whatever the value here, okay, for the r, okay, whatever is the value of r, so that is the direct value for the convergence, okay, radius of convergence. So it is similar to our given, or yes, it is similar to our solution here, or the answer here. So we have this x minus a, okay, the absolute value less than r, okay. So it gives you directly the value of r, which is 1, okay. So no need to do some transposition, or transpose, or do some solving it algebraically, okay, because it's already given the value of r, okay. Because you may encounter some cases like this one, okay. So the limit, sometimes you will encounter this one. So let's say we have x over 3, the absolute value x over 3, and since you all let's say you also use ratio test here, okay, you evaluate the limit, you evaluate the limit, and the answer is x over 3, the absolute value, okay. And since you use ratio test, you will form an equation or form an inequality which is less than 1. Okay, less than 1. So in this case, you just simply isolate the x, okay, by multiplying both sides by 3. Okay, when we say isolate, we just need to remove the constant or the coefficient here, which is actually it's 1/3. Okay, it has a coefficient 1/3 and remain, okay, or have an expression only with x. So we have the absolute value of x less than 3. So at this form of inequality, the radius of convergence will be 3. Okay, so yeah, so that's how you get the convergence or the radius of convergence. Again, if you're, let me erase all. Okay, if you have an inequality written in this form, x, the absolute value of x minus a less than r. Okay, so whatever is the value here in the right side of the equality, this is the left, right, this is the right. So whatever is the value in the right side, so that represents your radius of convergence. Okay, no need to do some transposition or solving algebraically here. Okay, however, if you have this certain case of limit, that is the absolute value of x over 3, okay, so over less than r, okay, you just simply isolate the value of x. Okay, it should be isolated, or in other words, it should be x expression only here in the other side. Okay, or equate it to absolute value of x. Okay, okay. So we already have our interval convergence, which is this one. Okay, and our radius of convergence equal to 1. Okay, next, last step. So we need to determine the convergence at the endpoint of interval. So the endpoint based on our interval of convergence, so we have this endpoint 0 and 2. So let's evaluate if this 0 is using x equals 0, will it converges or diverges? Also this one, the other endpoint, using x equals 2, okay, will the series diverges or converges? Okay, so to do that, we simply substitute each endpoint into the general formula of the Taylor series, then simplify. So given our x is equal 0, we have this general formula of our Taylor series. We substitute x, okay, by 0, so we have this, okay, and then we simplify it, we arrive to this answer. Okay, actually when simplifying, okay, we already doing some tests, okay, and that test is called comparison test. Remember the comparison test? In comparison test, from the original let's say from the original summation of a sub n, we derive our second series, which is the summation of b sub n. Okay, and from this b sub n, we use certain tests, convergence tests, okay, to determine if this series, this b sub n, will converge or diverge. And if b sub n converges, so does this a sub n. if B sub n converges, so that's our A sub n. And since in our given here, okay, if we're given here, we arrive to our A's, okay, this will be our B sub n, the summation of B sub n. Okay, from this, if we evaluate or use other tests, like what is the most applicable here? Actually, you can use P series test. Okay, using the P series test, the answer will be your series will be diverge. Okay, diverges. Okay, and since it diverges, so does this our original formula. Okay. Also, no, since it diverges, meaning if x is equal to 0, and we all know that it diverges here, so expect that in our notation, if you're going to get the write the notation for this interval, so we will use this bracket, this parenthesis. Okay, if the series diverges, okay, if the series converges, we will be using this bracket, this certain bracket, okay, box bracket, box, if the series converges. Okay, so we're done with x equals 0, so let's proceed to x equals 2. So if x is equal to, so we have this substitution of our x value in Taylor series. So next, we evaluate it, we simplify it, no? We arrive to this answer, okay, using comparison test. Okay, and then from that comparison test, we use another test. What is, I think the most appropriate here is using the root test. No, yeah, it's either root test or ratio test. And from that test, you will arrive to this answer, which is the series will converge. Okay, will converge. Will converge. And since the series converges at x equals 2, so expect that in writing the interval, we have 0, excluding 0 up to 2, and since it converges, we will use this type of bracket, which is box bracket. Okay, so here is it, no? So this will be the finalized full interval of our convergence. Okay, so to sum it up, so we have this x equals 0, no? And from that evaluation, the series diverges. At x equals 2, the series converges. Having from this information, we will have we arrive to certain point that our interval, full interval, will be 0 up to 2, okay, excluding 0 and including 2, okay, and the final answer will be this one, no? Our f of x, which is ln of x, is approximately equal, okay, to the summation from n equals 0 up to positive infinity of negative 1 raised to n plus 1 over n, yeah, it's n, actually it's n, yeah, times x minus 1 quantity raised to n, for x is an element from 0 up to 2, excluding 0, okay, and including 2, parenthesis 0 up to 2 bracket.